Alright, so we're going to be looking at the last set of indeterminate forms, right? We saw ones of quotients, those are really easy. Those of products, which were we needed a little bit more work. And these are the final sets, those that are raised to a power. So 1 to the infinitieth power, 0 to the 0th power, and infinity to the 0th power. And what we're going to do is kind of formulate a method that will work to any of these and then apply it to real examples that I'll share. So things with powers is kind of interesting because usually we have a function as the power instead of it being raised to like a constant number, right? It's not really like to the power of 2, it's rather to the power of a function of x, and then as the limit approaches infinity, for example, the power goes to infinity. So that's kind of a weird thing. The way we tackle this is actually through the use of logs, right? So this is a little bit of a review, right? If we have a log to a power, right? Let's say any power. Let's say this is g of x, right? Raised to the power of f of x. What we can do is use the power rule for logs, right? And what the power rule for logs says is basically if we have an exponent inside the natural log, we can bring it out to the front and it acts as like a coefficient. And then from this fact, we can turn this into a quotient pretty easily by doing this and dividing it by the reciprocal of it, right? So if we think about this as simplified as possible, we can go back to this. So this is kind of the idea. We can get it to a quotient pretty simply by taking the natural log and then doing that to it, and then seeing if it's indeterminate form that's a quotient, and then if so, then we're pretty much set, because all we have to do is use L'Hopital's rule. So we're going to be looking at three examples using these types of indeterminate forms just to see how they're done. Alright, so this is the very first example we'll be looking at, and as always we have to plug it in directly. So this is 1 over infinity, which is 0, so this is 0. So it's technically 1 to the infinitieth power. This is the indeterminate form. Therefore, we have to use, we'll soon have to use L'Hopital's rule, but first we have to try to manipulate it in some way to make us allow to use that. So we should look at the function that is actually taking the limit of, like this, right? If we take the natural log of that function, we have to basically take the natural log of this, right? 1 plus 1 over x to the x power. Let's do it write it like that, right? And since this is a power, we can bring this out, not here actually, we can bring this out even more here, right? This is the log property. So this is equal to x natural log of 1 plus 1 over x, right? And then we can further do this by making it a quotient, 1 plus 1 over x over 1 over x, right? Not too difficult. So now let's actually take the limit of natural log of f of x. So right, the limit as x approaches infinity of the natural log of f of x, we have to be clear that we're doing the limit of the natural log, not the limit of the function, is equal to the limit as x approaches infinity of this function. So I'm just gonna bring it over. No point in rewriting the whole thing when you can just move it over. So here we are. I'm gonna scroll down here now. So like this, there we go. So now we should just make sure this is an indeterminate form we can work with. The natural log of 1 plus 0, so it's just 1, divided by what? 1 over infinity, that's 0, which is 0 over 0. It's an indeterminate form. So therefore, use L'Hopital's rule, right? Not too difficult yet. And then what we want to do is just find the derivative of the top and the bottom, right? The top one we'll have to use the chain rule, so I'll do the outside first. So the outside is 1 over 1 plus 1 over x times its chain, so it's negative 1 over x squared, right? The inside function. And then we just want to take the derivative of the bottom, which is this. And then notice that these have a common factor, so we can just get rid of that. So we're actually just taking the limit as x approaches infinity of 1 over 1 plus 1 over x, which is when we plug in infinity, this term becomes 0, so it's just 1, right? But what did we actually find? We didn't find the limit that we were looking for at the beginning. We found something very close to it. And how close? We actually just found the limit as x approaches infinity of the natural log of f of x, right? Not the limit as x approaches infinity of f of x, but the natural log, right? So how do we get here to f of x? That's the question now. The way we do this is by remembering that if we were to take e and we raise it to the natural log of a power, right? Anything, this is like an anything type of thing. These things cancel out and we get x. That's how we're gonna go about this. If we have base e, right? Base e for both of these terms, so I'm just gonna move this over here. We essentially can cancel out the natural log and find the limit, right? We can bring the limit outside because it's a limit law that is basically proven. So it's just basically like this, right? Equals e to the first. This cancels out with this, and therefore the limit as x approaches infinity of f of x is equal to, let me just write out what it was so you will get a reminder of what it was. It was 1 plus 1 over x to the x is equal to just e to the first power, which is just e. And that's how we generally do these types of problems with the indeterminate powers, like what I want to call them. Alright, so this next example, we want to look at the limit as x approaches 0 from the right side of x to the x power. As always, we want to plug it in directly, right? So we get 0 to the 0th, right? But it's positive versions because we're approaching it from the right side. So it's really thinking of it as coming in from the right side. And this is an indeterminate form, right? Indeterminate. So that means we have to somehow manipulate it in such a way that we can use L'Hopital's rule. So first I'll define the function as x to the x, and then I'll take the natural log of that function. So I can get something better. It's actually x to the natural, x times the natural log of x, right? Use that little power rule for logs, right? And then now we can just take that limit. Remember, we don't have to change any things conditioned because the limit approaches the same thing as the original limit, so we don't have to change anything with this substitution. So we're finding this at the moment, which is just equal to the limit as x approaches 0 plus. And before I write what it is, let's actually write this as a quotient just to make things a little bit faster, like that, right? Not too difficult. Oh, this should be not limit, it should be ln of x over 1 over x. And then let's see if this is a indeterminate form, right? When we look at this graph right here, let's just draw a quick graph of that. Ln x looks something like this, right? Where we're approaching somewhere here, right? Negative infinity. We are approaching negative infinity. So now we approach it from the positive side here. Since we're approaching it from the positive side, we're approaching infinity, right? Infinity, not negative infinity, because that means we're approaching it from the left side. This is why we needed that condition in the first place, why it has to be the positive version, because of maybe this reason. Because if we were to approach it from the negative side, we would get a totally different answer. So, we're here. This is kind of an indeterminate form if you want to think of it like it. This is more of the indeterminate form, but if you want to think of it as, this is like a -1, right? And I mean, not like that. A -1 times that, right? So it's technically an indeterminate form times a constant, right? Times a constant. So if you want to think of it like that. So that means we can do this. This is a indeterminate form, right? So that means we can use L'Hopital's rule. Let me just scroll down here. Where am I? Right here. Use L'Hopital's rule. It's always helpful to state what you're going to do, so when you look back on your work, if you're double checking for a test, it's just so much easier to know what you're thinking of at that time instead of rethinking it over again. So limit as x approaches 0 plus, take the derivative of the top, take the derivative of the bottom, and see if we can plug it in. Let's see. If we plug it in, what do we get? We should probably simplify it first, right? We can simplify it here because we already used L'Hopital's rule. Let's see. If it's 1 over x and then times negative x squared over 1. I'm just dividing it out. So, oops. So this cancels and this goes to one term, so we're left with negative x, right? The limit as, I should write it here, the limit as x approaches 0 from the positive side, the limit as x approaches 0, that's a weird x approaches 0 from the positive side of minus x. And if we approach 0, we're ending up to be at 0, right? That makes sense. Again, we did not find the limit, the true limit of what we're supposed to be looking for. We found exactly the limit as x approaches 0 plus of the natural log of that function, right? And that's 0, so then to fix that we raise it to the e power, so that means f of x, or the limit, I should say, as x approaches 0 plus, is equal to e to the 0, which is 1. So that's the answer for the second problem. So as you can see, same process, just a different indeterminate form. So we're going to do one more. Okay, here's our final one, and we're just going to see how quickly we can do this, or like how much we know how to do this. This is pretty much the same thing over and over again, like kind of like repeating the same idea. So if we plug in infinity, again we get infinity over 1 over infinity. This is an indeterminate form. Indeterminate form. Alright, so I want to take the function and then the natural log of the function, which is 1 over x times the natural log of x, right? Not too difficult. And then I want to rewrite this as natural log of x over x, right? This is already in a quotient, which is really good for us, right? It's already in a quotient, so I don't have to do much. So let's take the limit as x approaches infinity of this now. This is ln. And then this, we could plug this in. This is infinity, this is infinity, this is an indeterminate form. Therefore, we can use L'Hopital's rule because it's in the quotient form. So let's do that. The limit as x approaches infinity of the derivative of the top, 1 over x. The derivative of the bottom, which is 1. You plug in infinity, is basically the limit as x approaches infinity of 1 over x. And then there we just plug in infinity, we get 0, right? Not too difficult. And again, like always, we did not find the limit of the function, we actually just found the limit of the natural log of the function, which is equal to 0. And again, to solve this problem, we have to have it base e, right? Base e. So now we have it the limit as x approaches infinity of e to the power ln f of x. This cancels out, and we're left with the limit as x approaches infinity of f of x, which is e to the 0, which is equal to 1, right? Not a difficult problem, just the same process for these types of indeterminate forms. Remember, take the natural log, and you should be fine with these problems because they're not actually difficult. It's just that you have to remember what you're finding and stay organized, especially with these types of problems where you get kind of messy results, like the previous one where you had to like do the reciprocal and divide it. It's an organization. I think most people get that wrong, the organization part, because they don't know how to write the quotient as well as they should be. So that's it for this one. I think that's basically it for all I wanted to cover for L'Hopital's rule. Again, if there's questions, you can always fill in the form to ask me a question, and I'll probably make a video of it because of how many, I'm not getting like a huge influx of requests to do it at the moment. So if you send me a question, I'll most likely do it, pretty much guaranteed. So that's it for L'Hopital's rule, and we'll continue learning about calculus with a new unit, whatever it ends up being. So this is pretty much the end of L'Hopital's rule section.